I would like to thank Professors Ramon Sastre and his colleagues to invite me to talk to you about Frei Otto. It is really a privilege, and I'm really it is a pleasure for me to take part in this great master course in which his philosophy, Frei Otto's philosophy, and way of exploring forms and forces is so vivid, so lively, so clearly present. So I'm going to show you some basic ideas concerning his thought, his way of working, some pictures giving you an idea about the type of models that he built, the type of experiments he made, and the way in which he was exploring that close relationship between form, force, and mass, which were the main three parameters guiding his career, his during all his research. So let me share my screen with the presentation that I have prepared. Okay, does everyone see the presentation?
Yes.
Okay, yes. Good. So, light structures inspired by nature. There we have Frei Otto showing one of his models, a model of a multi-hinged arch in his workshop next to his home in Germany, near Stuttgart. We could say that he's of course a well-known German architect. Many people consider him also an engineer. Others consider him an inventor, a scientist. It's difficult really to classify him because he has made full use of many different areas of knowledge. He has had an approach to architecture which has not limited to architecture itself, but has always been open to other areas of knowledge, to other sciences, to biology, to history, to philosophy, to engineering, etc. So, in an exhibition that took place 15 years ago, in 2005, celebrating his 80th anniversary, that took place in Munich, in the Architecture Museum of Munich. The title of it was meant to be a summary, well, an overview of quite a rich and interesting, wider overview of his work. It was the title of that exhibition was Light Construction and Natural Design. So two ideas, two concepts that we can find in Otto. The idea of lightness and the idea of learning from nature. The principle of lightweight is another key idea that has been present since the very beginning of his career, trying to find means, ways, materials with the best performance, trying to transmit and support load with a minimum amount of weight, and trying to see how that happens in nature very often, in everyday physical phenomena that take place every day around us in everyday life. So trying to connect, therefore, basic parameters such as form, force, and mass. The lightweight principle, which forms would be the most suitable to make a structure stronger, lighter, being able to transmit the biggest forces with the least amount of mass material, and to the longest place possible, with the longest way, through the longest way. So this is two basic ideas that we can take from both Frei Otto and another pioneer of light structures, a French engineer, Robert Le Récollet, who taught in the States, in Pennsylvania, concerning light structures. Robert Le Récollet used to say that his target was to reach structures with zero weight and infinite span. This is, of course, impossible, a utopian target, but the point is that it has been a sort of ideal that has guided, has oriented the activity of engineers since the very beginning. When we see how structures have been evolving along history, always trying to reduce weight and span longer or breach longer spans. And another idea concerning structures, he said that the art of structure is how and where to put the holes, to build with holes, to use things which are hollow, things which have no weight. So this is really striking because he's talking about voids, holes, and he's talking about the art of designing a structure as the art of positioning the voids to build with holes. So we could think here of a human bone, for example. If we see a micro picture of a human bone, we will see that most of the volume is actually occupied by voids, by hollows, and a low percentage of volume in a human bone is occupied by matter. So that is an example of how this idea is not such a crazy idea, but something which is quite we can find quite often in our everyday life. So back to light structures. Frei Otto, what does he say about light structures? He says, lightweight construction is a way of building with a minimum consumption of material, energetic, and economic means. So I think I'm trying to, okay. So it's not just a matter of economy from the monetary or financial point of view. It's a matter of economy from a cosmic, so to say, point of view, something that connects very nicely with today's concept of sustainability. Concerning natural structures, we've been talking about light structures, natural structures. There is another author, Mathila Gika, who in a very interesting book, originally written in French and translated into English, The Geometry of Art and Nature, says that he underlines the principle of least action for the inorganic world and the principle of economy for economy of material for the organic world. So least action and economy of material. two principles present, active, in the organic and the organic world. And Frei Otto, concerning natural structures, says that the form of a structure, a natural structure, is the form of a structure which transmits the forces received to the supporting points with the least amount of material. Again, amount of material. And somewhere else he says that natural structures are structural systems whose construction does not derive from a planned process, but comes from self-forming or self-organizing processes. Now, this is a key idea. If we see as we are going to do his models and his explorations, we will see immediately that his approach is not to impose a preconceived idea on matter, on a certain material, but to see which forms does that material generate from different types of forces. So he explores in his experiments many different physical self-forming processes. Like, for example, just give an example of what we are talking about, a very simple example. If you take a chain and you hang it from both ends, the chain immediately adopts the most suitable form to work in tension, because that chain is absolutely unable to work in compression, does not resist any compression. So it adopts the form of a catenary curve just to make sure that all stresses are tension and no compression. That's a simple self-forming process. The material on its own itself has found the most adequate form to behave or to transmit loads in the most effective, most appropriate way. So here we come to the Institute of Lightweight Structures that was founded by Frei Otto in the 1960s in the University of Stuttgart. As you can see, quite an unusual form for an academic institution. It is actually a tent built out of a cable net, which was in fact the test model that was produced for the World Exhibition Pavilion, German pavilion, that took place in Montreal in 1967. That natural size, scale 1:1 test model that was built was used as the headquarters of that institute devoted to the research of lightweight structures. It can still be, it is listed actually, it is protected, and it can be visited even nowadays in the University of Stuttgart. Here we see part of the structure, the characteristic form of these light structures with these doubly curved surfaces that we can see here. Another characteristic element, which is this loop made up by a rich cable. We will see it more in detail later on, allowing light inside and also driving tension along one cable and preventing tension from concentrating on the upper vertex or vortex of the mast, which supports the tent. And here we see some of the cables which are anchored underground to counteract the tension force that is keeping up the tent. Inside the tent, we see models, we see members of the institute working with different types of structures, and this is the view of the loop I was talking about, which connects the cable net and distributes the tension of this cable net along the loop so that the vortex of the loop at the top of the mast that we see here, this is part of the mast, does not puncture actually the cable net, but distributes evenly that tension. We continue visiting his institute, and here we find a machine that was developed, invented by Frei Otto himself. It is actually a machine providing adequate conditions of dampness, humidity, and temperature to keep models made up with soap films as long as possible to allow, as you can see here on the right-hand side, cameras to take pictures from different positions, from different points of view. This is something that he developed in the 1960s. He worked with soap film models, which are, we will see later on, some of them are physical phenomena that develop minimum surfaces and with specific border conditions, and having to build these models with soap films. Soap film is a very weak structure. It breaks very easily, very quickly, and it therefore needs a chamber with damp and low temperature in order to allow these forms to stay. And here we see different forms of these types of models. You see, for example, here rings which are made up of wire. These are actually stiff borders which are submerged in a solution of soap and water. And once you take this model out of the solution, then this doubly curved surface, this anticlastic or saddle surface connecting these edges that we had made, circular and semicircular wire edges, the soap film connects them and develops a minimum surface. That's the minimum surface connecting these border edges. So that's one result. Another result is, for example, with this helicoidal rigid wire edge and this central vertical string. You submerge that into the soap film, and when you take it out, you get this form or this other form in which the edges, the border edges, are no longer rigid. Well, the supports are rigid, but these points are connected with strings, with flexible strings, very thin strings. Then you take all this model down into a soap film solution. You take it out, and then the solution connects all these edges, which are, as you can see, flexible. They are not rigid. And there you get another minimum surface connecting them. A minimum surface is another physical self-forming phenomenon in which the surface is extremely thin. As you can see, it's a membrane. The result, the form which is the result of the experiment, is a thin membrane which is subject to tension, no compression, only tension, because it's the only way that a soap film can work. That's simply because of its physical properties. And there we can see other surfaces developed also by soap film. Here we see, for example, another geometry, another type of alternating doubly curved anticlastic or saddle surfaces, which are made up by connecting strings, making ridges and valleys. Here we have these upper points which are connected with these strings, which are actual ridges, and lower points, which is this and another one here, which are connected with other strings, which make up valleys. So here we have convex curves, concave curves, and between them, connecting them, and also here at the edges, we get these doubly curved anticlastic surfaces, which are connected to the neighbor ones, the next one, and this one. So we have here a sequence of alternating valleys, ridges, valleys, and doubly curved surfaces, which at the end make up the roof of covering a span, the span between these two rows of supports. Another type of physical phenomena explored by Frei Otto are bubbles. Bubbles, either surface bubbles, as we can see here, or three-dimensional bubbles, foam, a type of foam. So which are the patterns that develop with film, with this soap film making these bubbles? This could be, for example, oil in water. You know that it makes bubbles. So you see here three different patterns of surface bubbles. One specific pattern of three-dimensional bubbles. They are sort of polyedra made up of soap films with a type of foam. And this scheme here is also a model made up by soap films, but it's very interesting because it is the solution of a mathematical problem, which is the minimum network of ways connecting a number of points. Here we have 1, 2, 3, 4, a number of points, okay? And we would like to know which is the minimum network of ways, the minimum way that would connect all of them. Here you have it. And this has been developed by a soap film. How has this model developed? We have these supports with these points have been submerged into a soap film solution, and a screen has been put at the top of that solution. So you take up these points with the flat plate, and between the flat plate and the surface of the soap solution, these vertical membranes develop. And they themselves, of course, the ideal thing would be to see a video to see how these actually developed. Because where as you take up that flat surface, these vertical membranes developed, and they make up, at the end, they result in this network of a minimum network of ways connecting a number of points. It's a mathematical problem solved by a physical phenomenon in which soap films are the protagonists. That was invented and developed by Frei Otto. Other type of experiments and models are grain hips. Which forms do hips of grain develop when you, for example, you take a cube in which you have a grain and one hole. That hole allows grain to pour down and create a sort of mountain with the adequate slope. You know, this is the natural slope according to the material. And you see how this form develops, and also this form, a void and a solid. So at the end, you get these two forms. Now, when you do this with a number of mountains, you get these forms. Instead of one single, you connect different hips of grains of, for example, sand granules, sand grain. Here you get different forms. All of them are the result of a physical phenomenon, a physical self-forming process. Another type of models or experiments, viscous fluids, or for example, glue. Here you have, or honey. You take honey, you put honey between two flat connecting surfaces, and you try to separate them, and these are the forms that develop. Or you take glue and you connect different nails, for example, at the top of a surface, and there you get a branching pattern here. This is a closer look of a bone. That is what I was telling you before, in connection with the branching patterns that material develops in a human bone, and the amount of void, the amount of hollows that you find in a bone. Other type of physical phenomena and experiments developed by Frei Otto is folding. We find folds everywhere, every day, around us. But have you ever thought how many different types of folds there are, and which are the ways in which they develop? We can make them develop. That is something that that is a question that Frei Otto raised, and he explored, as you see, different materials. Here you have paper, rinking paper, a piece of paper. Which are the rings? Which are the folds that develop? Or a piece of cloth with a wind blowing underneath. Which folds are developed? Or a hanging piece of cloth, which different types of folds can be developed? So by exploring folds, he developed deployable structures, roofs made up with pieces of cloth with extending membranes that can be folded out and down, can be developed, deployed, and as you can see here, either making the radial foldings These are radial fondings or linear, rectilinear, straight of folds made up by running along a rectilinear straight line. This is a model of another of Frei Otto's inventions. That was invented well, quite early in his life. He was 25 or 26 at that time, in 1950, when he developed this model. It is a multi-hinge arch. Well, the theory of structures says that when an arch has more than 3 hinges, if an arch has 4 hinges, then it collapses. But Frei Otto, in his experience in life, you know that he took part in the Second World War as a pilot, and he saw ruins of structures, ruins of walls and arches, and he saw arches with more hinges than the theory he had learned. And so he thought, well, why is it really possible to build an arch with many hinges? And that's the model that he developed. You see that the voussoirs, or the different parts of the arch, are made up by convex pieces of surfaces. Convex surfaces, they are singly curved surfaces, convex to each other, and therefore connecting on one single line. This piece with this piece connects at this point, this with this one at this point, this one with this one at this point. So the thing is that the weight does not surpass the final point, but either end of the pieces, either end of the voussoirs, either here, or there. As long as the connection point is within the thickness of the model, it is stable. And at the end, you get many different thrust lines, many different straight lines, curved lines for the different types of arches developed with this model. Thrust line is the line which connects, the line through which force goes from one piece to another. And by connecting these points, you get the thrust line. Other inventions by Frei Otto, always trying to make the most out of the least. That was also part of his experience in the prisoner camp in Chartres in France, where he stayed for 2 years after the end of the war, from 1945 till 1947. Much scarcity of means, of materials. How to build a bridge with rests of railway metallic elements, for example. How to build a column just with extremely slender elements, slender masts, by bracing them at intermediate points, as you see here. So here we see a combination of compressed masts and tensioned cables, creating an overall slender mast. Here we see also a picture of our column, the human column at the back, which somehow reminds one of these type of structures. And that's actually also the source of inspiration for these type of models that he also developed. A hinged mast, or as he called this, a mobile arm. You see a core which is made up of a steel slim element here, these triangular plexiglass elements, and these tensioned cables that allow you to control this hinged mast or mobile arm. You can move it in different directions depending on the strings that you are pulling at the bottom. And also another structure that he developed. This resembles very much this when Buckminster Fuller, a great friend of Frei Otto, saw these models. He he also saw pictures of pictures taken from microscopic creatures like radiolaria, for example, or pieces of bones. And there they found that the patterns developed were very similar to the ones that he had developed here, for example, this sort of a space lattice with fixed joints. Another type of model is branching structures. These are made up by applying the inversion principle with hanging strings. There we start with this point. Here we have strings branching from this point and until that point, and that from that point another group of branches here, so that you get at the end this grid of points from this point to this grid through an intermediate group of branches with different levels. And these are hanging loads. These hanging loads are tensioning all these strings and are another physical self-forming process, because this load is giving the actual slope and the final form of these for these strings. And if you are sure that they are working in tension because they are not able to work in compression as they are hanged, then you invert it and you get this branching pattern in which all the different bars or elements should be working in compression. So loads coming from, we could only talk about gravity here, vertical loads, no horizontal, no wind, no earthquake, only vertical. The form shaper, the element that is shaping the form of these models and these structures is gravity. So here we have this branching structure developed, as you can see, with 1, 2, 3 branching levels from here, from the bottom till the top. And one real structure built with this type of branching model, branching structures you find in the main hall of the Stuttgart airport, was not designed by Frei Otto. Frei Otto, we must say that he invented new types of structures with his experiments, with his explorations, but it was in the collaboration with other architects who actually built these real size structures, like this Stuttgart airport. But of course, without the inspiration of Frei Otto, this would be inconceivable. Pneumatic structures, different models also. These are models that we can see. We can, if we visit his institute in Stuttgart, his tent. As you can see, different patterns developed with these doubly curved surfaces. Of course, always trying to reproduce the form of a membrane which is inflated, and as you know, a pneumatic structure is able to span, to reach a span, to cover a space, thanks to the physical phenomenon of the different pressures, air pressures that we get inside and outside. If there's a higher pressure inside than outside, then the thin membrane will stay up, will stay in position to behave as a roof. Another model that we can find in the famous Frei Otto's tent, his institute, is this model, a three-dimensional model of the Pantheon in Rome, this famous Roman structure that still is standing nowadays since the 2nd century, with a span of 43 meters and 30 centimeters that was not surpassed until the 19th century, when new materials like wrought iron were developed. So Frei Otto was trying to find out why the Pantheon was stable, and which was a relationship between a funicular form, a funicular hanging form, and the form of the Pantheon. This is always an interesting issue, because we see that along the history of architecture, vaults have adopted very specific forms in Roman times, in Romanesque architecture, Gothic architecture, very often based on the simplicity, geometrical simplicity needed for construction purposes, but seldom taken into or trying to wonder which one would be the most suitable form to behave or to work in compression only. So there we have the funicular forms, these hanging models. All of you are familiar. I'm sure all of you know the famous Gaudi's models, hanging models. Now the thing here is that these models developed by Frei Otto are three-dimensional. They are strings, hanging strings, which do not stay on one single plane, but are also developed along the base of the Pantheon. And if you can see, you will notice that this is, which is, once you apply the loads at specific points, trying to reproduce the actual loads, gravity loads, you see the final form developed within the thickness of the actual structure. And that would be the reason why it is stable. And on the other hand, the separation, these stresses, which in this case are tension, but if you invert the structure, that would correspond to compression, which indicate that the dome, the semispherical dome, is compressed along the upper hoop lines, but tensioned along the lower hoop lines. That's something that was known because cracks usually appeared with this semispherical geometry, with this type of domes. But there you see always this model I wanted to show you just as a way of seeing how Frei Otto worked with them to explore the actual structural behavior of such historical structures as the Pantheon. Now, this is a summarizing scheme showing different self-forming physical processes. We've been seeing several of them used by Frei Otto and classified in accordance with the generating forces. This has been taken from one of the books published by the institute founded by Frei Otto, which is devoted to the different types of experiments that he developed. These are physical process in which tension is the protagonist, starting from a simple cable being pulled apart from both ends, or a chain being hung from both ends, or a simple straight vertical line with a weight at the end, or these minimal waves I showed you before, or that these minimal surfaces with two upper points and two lower points developing with a soap film model, for example. Soap films, branching of viscous liquids, cable nets developing minimum surfaces. These polyhedral foams we saw also, tight packing. Compression, the multi-hinged arch we saw, the inversion of the catenary, these arches, and other arches, other suspended nets that we will see also later on. Well, I see that we are running out of time. We have only 5 minutes left. I'm sorry that I have been a little bit too slow, maybe. But
it's fine, Juan María.
Yeah, I just wanted to show you, although in these 5 last minutes, at least 2 types of structures which are very innovative, very interesting, and I wouldn't like to finish without talking to you about them. Okay, well, here this is another classification of these same physical phenomena based on on the generated forms. We saw earlier the forces, and here we have the resulting forms, either linear or surface or spatial elements. Okay, so let me go down in my presentation. I miscalculated the time. I just wanted to show you so many things that it's impossible in 1 hour. Okay, this would be very quick. Hopefully, I promise. What is the problem of these of a membrane surface? It's not a problem. The problem is not weight. It is an extremely light structure. The problem is form. Is to make sure that form stays. When you have a flat membrane that is being pulled along the edges, and wind is blowing, it flaps. So how can you stiffen that thin surface? By doing this, by form, by making that flat surface adopt this saddle form, this doubly curved anticlastic surface, 2 lower points and 2 diagonally opposed upper points. This makes sure that every point is subject to 2 opposing forces, one trying to connect these 2 lower points and another one trying to connect these 2 upper points. So these 2 acting opposing acting forces stabilizes the position of each point of this membrane. So here we have this basic curved 4-point tent developed by Frei Otto in 1955. Here you have the soap model film, which inspired it. This is the undulating minimal surface with parallel ridges and valleys that I showed you earlier. These are the lower points, these are the upper points, and this is the resulting doubly curved undulating minimum surface, which also gave rise to different types of tents, parallel wave tents or star wave tents. Here you have a real parallel wave tent built for a garden exhibition in Hamburg, 1960s. This is a real structure, the airport of Denver Airport, 1990s, made up with this type of parallel wave tent developed by Frei Otto. This is an undulating minimal surface with radial ridges and valleys, a soft-fill model. Here, the ridges and valleys are not longer parallel, they are radial. And here we have a real structure, a real star wave tent designed by Frei Otto in the 1950s for a garden exhibition that took place in Cologne. It's a beautiful, really an extraordinary structure. And it's all made up by masts, light masts, cables, and textile membranes. This is the plan, the cross sections of this dance pavilion. Another type of tent is the arch-supported tent. You have an arch which is being compressed by these tension membranes. A real structure, which was the entrance arch to this Federal Garden exhibition that took place in Cologne. And this is the inspiring model made up with soap film, a minimal surface that we saw earlier. Plan, cross-section, pictures, antifunicular forms, hanging chain net models, of course, the models of Gaudi mentioned. This is a workshop that we make here in Valencia with our students at the School of Civil Engineering, because it's good for, I think it's good for them to see also how gravity shapes form. It's a simple piece of cloth that is soaked in plaster, submerged and immersed, and then you leave it on. It's very beautiful to see how the piece of cloth, which is a simple piece of cotton, which has no weight, nearly zero weight. So you see the form before it is soaked in plaster. When it is soaked in plaster, it is actually loaded. And when it is loaded, then you get the real continuity of these funicular forms, of these edges, these border edges, or these groins, these ridges. So there is a difference between this and this. The difference is that this is not loaded, this has been loaded, and therefore it is an real anti-funicular form. You invert it, and yet you get these beautiful inverted models with these funicular vaults. And you can make all sorts of variations, different types of arches, different types of spans. And here we see a picture, historical picture of Frei Otto in the 1950s in University of Washington, with another funicular structure, rubber membrane hanging from 6 points, evenly loaded by these nails, or yet another, this other type of hanging net from 8 points, which is stiffened by polyester resins while it is being hanging, and then once it gets dry, then it's inverted, and that you get these forms, which you also get when you get a hanging chain net. This is another interesting new type of structure, not just one single chain, but a chain net. When you get a chain net, you get a three-dimensional form made up by linear elements, which are working in tension only. And as you graduate the borders of this chain net, then you get this continuous doubly curved synclastic surface, which is the model to create a grid shell. And there we come to another great invention, another great structure invented by Frei Otto, a structure made up with wooden or timber laths or slats, which takes the form of a hanging chain net. This is a model made up by chain laths, one type of grid shell, a grid shell, which is made up of a grid of laths And there you have at the bottom, connecting with the ground, a continuous edge. This is one of the first real model, grid shell model that the Frei Otto developed in Essen the early 1960s. As you can see, it is a doubly curved synclastic shape that develops from a flat slat grid on the bottom, on the floor, on a horizontal floor. You put this flat grid, which starts like this, with these squares, and these hinges. These are hinged connections, nuts and bolts, which are not tightened. They are loose. So the thing is that you hoist up these laths and to the level, to the height that you have calculated with a hanging chain model. Then these points rotate. At these intersections, the grid rotates, and the initial mesh, which were made up by squares only, transforms or deforms into rhombi, different types of rhombi. These are sharper rhombi, and these are less sharp rhombi. But what you get at the end, there you see the process. You get the flat grid, the flat wooden slat grid on the floor, a square mesh. You hoist up specific points of the grid, and then the intersections move, rotate, because they are loose. And once you get the desired position, then you tighten. You tighten all the hinges, and when you tighten them, you connect also at this point. This is one type of grid shell, a grid shell with a continuous edge at the bottom. Then you get a fixed structure, a fixed vault, which Frei Otto named a grid shell, because it's a thin shell, but made up from a grid, and even lighter than a thin reinforced concrete shell, and having the advantage of allowing light inside. It's very similarly as a ute does with this grid, or other more primitive or vernacular structures. So there you see the hanging model, and there you see another grid shell developed by Frei Otto, in this case with reinforcing bars, reinforcing steel bars, that took place in Berkeley in the States. You see more in detail the connections, the points where the hinges are tightened, a model with the original flat square mesh grid deformed and developed into a doubly curved grid shell. And this is a picture showing one of the greatest grid shells that were built, that Frei Otto designed and built for this federal government show exhibition in Mannheim in 1975, with spans longer than 60 meters at this point, and with forms unconceivable at that time. These are not capricious, whimsical forms. These are anti-funicular forms, forms that have been developed by a hanging chain net model. This is the model from which these forms were taken. And once you get the heights at this specific points, then the grid, which is deployed on the floor, is hoisted up at specific points. And when it is hoisted in position, then all the hinges are tightened. This is a double layer grid shell, and you get incredible, nice, doubly curved synclastic and anticlastic forces, producing a vault full of light. It was covered with a thin membrane, thin transparent membrane, 6 meters span, extremely light structure, and some details, some pictures that I took when I visited this formidable structure. So, well, and this is a grid shell that I built myself with my children in summer with reed and with string, strings, diagonal strings, to make this grid curve and adopt the synclastic doubly curved form. So I stopped here. Because I had many more things, but it's longer than 1 hour. Sorry for the 10 minutes that I have surpassed the hour. Thank you for your attention. I'm open for any comments or questions that you may have. It's impossible to summarize in 1 hour all the richness of the work of Frei Otto. Yes, thank you to you.
Okay, no, the good thing is that we have to invite you again. So for more lecture. Okay, so
Yeah.
it was a really impressive lecture, and I think it was very well related, and there are things that we were all very happy to be seen and from another point of view. So I think very nice explanation. So I'm going to leave the students if they have any question. Now is your opportunity. Okay, if not, I'm going to ask you, how did you get in contact with Frei Otto World? Did you have the chance to meet him?
Yes, I met him while I was writing my doctoral dissertation in 2004. I went to visit him to his home in Stuttgart and his workshop. He showed me his models. That was a great privilege. And you asked me why I became interested in Frei Otto's work.
How it happened, and were you working in
Yes. Yes, the thing is that I started teaching here at the Polytechnic University of Valencia, in both at the School of Architecture and the School of Civil Engineering. I had to teach different subjects in which the pupils were, on one hand, architects, and on the other hand, mostly engineers, civil engineers or structural engineers. So I found in Frei Otto a beautiful, a great combination of both worlds. An example really interesting for both worlds, for both professions, for both schools. So that's basically the reason why I developed an interest in Frei Otto's work.
Yeah, I think it's a very nice decision. Actually, after so many years, it's still incredible how in School of Architecture, especially, teachers are insisting in deriving forms out of designs, what you were calling whimsical forms. It's like
Yes.
forms, whereas we have these examples of how you can design processes. And actually, I think the one big difference between copying natural forms, like people tend to do. If you say, I'm doing biomimesis, and you just copy forms, I think the main legacy of Frei Otto is like the effort of understanding the processes.
That's right.
To be compound given certain restrictions. So I think it's a beautiful lesson, and especially in terms of schools of design, it's something that it is surprisingly slow to change. Like teachers are still imposing forms, not always efficient, with aesthetic criteria only. So
Yes, yes. This is something that Frei Otto has very often talked about, because he has been very often asked about his intentions. Did you, Mr. Otto, did you intend really to copy or to imitate nature? And he always denied that, because he said, no, what I'm trying to do is to understand nature, not to copy it. Is your roof for the Olympic Games, your roof that you designed for the World Montreal exhibition, a copy of website nets web nets? Well, it was not. It was actually not. What he was trying to do was to really see how these how these materials, by these physical phenomena, developed their forms. So he built structures, he said, to understand how nature behaves, how nature works. And and a real proof of this is how he um, worked with people within the field of biology from the very beginning, from the early 1960s. He worked with, for example, a biolog that was very famous in Berlin, where he started teaching. And he founded a group which was named Biology and Construction, trying to explore how creatures, small animals, develop their structural forms. For example, radiolaria. Radiolaria are a type of very small microscopic algae. When you see them through the microscope, you see the patterns developed by the strong forms that they develop. And even the spider webs, the webs that the spiders build, how strong they are in relation to their size and their weight. These explorations were also very important in Frei Otto's work. And also the importance of modeling. I mean, there are so many things really which are so interesting. Models, the importance of models, of building physical models. Frei Otto used to say that when you work with computers, of course, you can get unexpected forms, but the computers behave as they have been planned to behave, whereas nature behaves in a way that we humans still do not know in full. We still need to explore nature more in depth, so we can find out, we can discover things from natural phenomena, from physical modeling. And it was interesting to find how the materials that he used were taken from everyday's life. Soap films are not so difficult to find. Spider webs, bubbles, sand grips, foldings patterns. These are things that we find everywhere, every day. And the importance given, attached to models also, I think comes from a tradition that one can trace in countries like Germany, and it's more difficult to trace in countries like ours, like in Spain. When I go to the workshop here in our school, and I see foreign students working with models and Spanish students, you see a difference in the fear that the students experience when having to handle tools and materials. German students usually don't really fear so much, tools, because they are used to use them. They are used to building models, to building physical models. Whereas our students in Spain are not so used to that. So that is very much in connection with what you were saying at the beginning. And also with the tradition of model building. The tradition has gone to the extent of developing a theory of structures which is specific for models. So there is in Germany and at the University of Stuttgart, a group of people with which Frei Otto worked with the Modellbaustatik. Modellbaustatik in German means theory of model structures. So structures, of course, do not behave the same way in models as in real scale. So you have to calculate according to the scale of models, and they develop a theory of structures for models, for modeling. And they build, for example, models with microscopic micro-concrete models, and specific institutes, research institutes for model building. Different types of models, models for form finding and models for stress calculations, deforming calculations. These are different types of models, for example, that were used in the Olympic Games structures. They developed models to calculate deformations and to calculate stresses, which were quite different from the models built for form finding. Well, I mean,
that's definitely something very, very challenging. No, like things doesn't grow or doesn't decrease always linearly. On the contrary, they can be power to the power to 2 or power to 3. If it's mass or surface, so yeah, it's very, very challenging. And I think there's a lot of science and also a will in not only relying in digital models. So I think it's really fundamental to use it, to build it, because it's you learn plenty other things than just digital models.
yes, yes. I would like to ask the students, would any of you, has any of you ever had the opportunity of building such type of models, a model of a funicular structure or a hanging model, or I don't know, a light structure model?
Hello, we have a class this semester with Dr. Ramon Sastre.
Yes.
Yeah, and we were experimenting with models, tensile structures, and it was very interesting, at least for me, because it was my first time doing these models. Because when I was taught architecture, we didn't work with tensile structure.
Great.
So that was my first time, and it was a great experience. But only for me, the only challenge was there are infinite of forms you can create in this space with this tensile, and which form you pick and why are still questions for me. But it's this interesting approach and design process.
Yes, yes. It's like a game, really. You can play with many different possibilities, many different variations, and then try to classify what brings different classes, different variations, what type of parameter. Parametric design, not only parameters from the point of view of mathematics, which is also great. You can also derive and develop many different forms, but also from physical parameters. Yeah. Yeah. Yes. Would anybody else like to say something about his or her experience in connection with this type of structures?
Well, I'd like to ask you something.
Yes, please.
But, what do you know Frei Otto would do now? will he be like superpowered with these new tools, these computer tools? Because he, well, we of course we are nourished from his knowledge, and well, he's like primitive to us in this parametric design. But what would he have done with our tools?
Yes. I have been stressing physical models in my presentation, but that doesn't necessarily mean that Frei Otto did not use computer calculations and did not work with mathematicians. He did work with mathematicians as well. As I told you before, he tried to solve a mathematical problem with these minimum ways. And also he worked with colleagues in his university, mathematicians who were familiar with computer calculating, and who really managed to develop a mathematical model for those anticlastic saddle surfaces that he was developing with his models. Of course, that took place years ago. The prospects that we have nowadays with computers, with the programs for parametric design, are quite different from that time. Much more powerful, many more possibilities. He undoubtedly, well, you know that Frei Otto died 5 years ago, but he undoubtedly, I'm sure that he would be very glad and very ready to continue working with parametric and computer design, because he was open to other areas different from physical modeling or analogical models. So he would really appreciate that. But I think that it's also important and good to underline the idea of not forgetting, not leaving behind physics, real physical reality, analogical modeling.
Yeah, sure. Thank you.
Thank you. Thank you for your question. Yes.
Hello.
Yes.
Yes, I just wanted to comment that right now with the tools and the technology we have, like 3D printers or laser cutters or CNC machines,
Yes.
it's quite very fun to try to get these shapes. For example, we were trying to get this grid shell. I don't know if you can see.
Yeah.
I use a 3D printer, the surface, and also I use the relaxing grasshopper. That was very funny. I enjoy very much, and I am enjoying very much this this master using these parametric tools, and is also a big opportunity to combine with digital fabrication right now. I think Frei Otto work that he did at his time, it was much harder than right now, and now we have more tools to get more interesting shapes.
Yes, yes, of course, that's great. These models that that you made, so I congratulate you. Really impressive structures that you can build with 3D printing and grasshopper rhinoceros programming, which can give you forms produced right away with a computer. But of course, having used the laws of these funicular forms, for example, and the models used with hanging materials, it's great to combine both means without forgetting one from the other. Yeah. Great.
Okay, Juan Maria, I think we can call it a day. We can close the session.
good.
It has been a real pleasure for us having you in the master. I think
I've enjoyed it. I've enjoyed it very much. Thank you very much to you.
All right. So see you next time. We will try to be in touch and try to invite you as possible.
Definitely. Okay. I will be very pleased. Yes.
Okay. So thank you very much to all of you, and see you soon.
See you soon, and all the best to all the students in this master course.
Thank you.
Thank you.
On your work. See you. See you. Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye.